In Lesson 4.4, the fundamental theorem of calculus, we'll explore how to use the integral to find the area under any curve between any two given values. Essentially, we're just going to generalize what we did back in Lesson 4.3, and hopefully it'll make a lot of sense. Once we take a look at the fundamental theorem, we'll see how to apply that by using the average value of a function, which also will make a lot of sense when we get there. And based on our average value of that function, we'll use the mean value theorem for integrals, which I'll explain when we get there. Once we cover all this, we'll take a look at the second fundamental theorem of calculus, which is essentially an accumulation function. That is, it's a function that adds up all the area as we go along. There's lots of applications to physics, so hopefully you've learned about things such as work, which involves an accumulation function. Anyhow, all this being said, why don't we begin by exploring the actual fundamental theorem of calculus? It's a beautiful thing. We'll use it the entire rest of the year, and let's go ahead and take a look at it now. So, as I already said, the fundamental theorem of calculus is used to find the area under a curve between two values somewhere. So, let me go ahead and draw what this curve looks like. It really could be any curve. So I'm just going to draw some general curve that looks like this, and I'm going to call that curve f of x. Now, let's say we want to know the area under the curve between here, which I'll assign the x value of a, and here, which I'll call b. How do we do this? Well, it's actually very easy. All we're going to do is integrate f of x, and we're going to plug b into that integration. What that will do is it will give us the area all the way from 0 up to the value of b that we stick in there. So it'll give us all of this area right there. Well, that's not the area we want. It does go up to b, that's cool, but we only wanted to start at a. So what I need to do then is go back and plug a into my integral. That will give me the area right here from 0 up to a. Now, how can I use these two values to find the area of the remaining red region? It's actually very easy. We're just going to subtract them. And so what I'm going to end up with is the integral of f with b plugged into it minus the integral of f with a plugged into it. If I subtract those, that will give me this red region right here from a to b. And that's exactly what we want. And that's exactly how it's done. We simply integrate, and then substitute in, substitute b, and subtract the two values that we find. Maybe it's a little bit confusing theoretically, but if we do a couple examples, I guarantee it's going to make a lot of sense. So let's take a look at example A right now. So in our first example, we're going to integrate the function you see here, t cubed minus 9t, and we're going to integrate that to find the area under this curve between the x values of -1 and +1. So let me show you how it's done. It's really not too bad. What we need to do is we need to integrate this internal function. And if we do that, what we'll get is simply t to the 4th over 4 minus 9t squared over 2. And when I want to evaluate, what I do is I draw this vertical pipe, as it's called, and I put my lower and upper bounds here and here. Now I can go through and actually work this out. If I plug 1 into this, I'll get 1/4 minus 9/2. So I'll work that out in just a moment. And then I'll subtract whatever I get when I run the -1 through that. If I run -1 through, that will give me 1/4 minus, well, 9/2 again. Very interesting. And if we work this out, this ends up being -17/4 minus -17/4, giving us an area of 0 somehow. Now, how could that possibly work? How could we find an area that's equal to 0? Well, here's how. If you take a look up above, there is a graph of the function that we're working on. And in fact, if we take a look at this, if we're integrating from -1 to +1, this is the area that we're looking at. This area back here, and this area down here. So why does the area end up equaling 0? Well, if we take a look, this area right here to the left is a positive it's a positive 17/4, And this area down here is a negative 17/4. So essentially those two areas are canceling each other out, giving us an area of 0. Now, if the problem actually asked us to find the area per se, what we would do is try to make this second half right here, make that positive. So we would do an absolute value of that. And what we'd end up is 17/4 doubled, or 17 halves, if you will. However, this example only asks us to evaluate the definite integral, and we've done that. And we've got an evaluation of 0. Let me pause for just a moment. Definite integral, what do we mean by that? Well, when we did the indefinite integral, that was simply looking at any two values, which is why we had to add that plus c. We weren't sure how high or how low it went. But with a definite integral, it tells us we are absolutely going from x equals -1 to x equals +1, as we've done in the picture up there. And so you see that a definite integral certainly can have areas that cancel each other out. Well, with all that behind us, let's take a look at one more example, example B. And certainly at this point, I'll encourage you to pause the video and try that example on your own. But we are going to forge ahead and do it together right now. So our second example is a fun problem. If you take a look at it, you can see for yourself. Now, to be honest, I'm not going to integrate it as we see it here. I'm actually going to play around with it a little bit. I notice that there's a 2 on the bottom. That's a scalar multiplier. I'm going to pull that out as 1/2. And furthermore, I'm not going to leave the inside the way it is. I'm going to, simplify it a little bit, make it easier for me to work with. X minus x squared over the cube root of x. Well, we can rewrite that. This is actually going to be x to the 2/3 minus x to the 5/3. And if you play around with it a little, you'll see where I got that from. Nothing bad to deal with, just kind of ugly. So we can go ahead and integrate this now. The 1/2 is going to stay by itself. I'm not going to mess with that. But this x to the 2/3, if I add 1 to that exponent and then divide by whatever I get, this is actually going to say, let's see here, we'll have x to the 5/3 divided by 5/3. And I'm not going to do divided by 5/3. I'm going to simplify it a bit and write it as 3/5. That will be easier to deal with. And I'm going to do much the same with this x to the 5/3 here. I'm going to call this x to the 8/3. And when I divide by 8/3, that's going to be the same as multiplying by 3/8. Now, I'm going to go ahead and evaluate that from -8 to -1. And let's see what happens here. This ain't going to be pretty, but it will work. I'll start by plugging in my -1. And if I do that, what am I going to end up with? Well, this will just be, let's see, -3/5. And this will be minus 3/8. So that wasn't too awful. However, I will need to subtract whatever I get when I plug in my -8. And just to keep things all intact, let me go ahead and put brackets around this. So it's 1/2 times all of this stuff. Now, if I do plug in -8, I did this beforehand, and what I ended up with was -96/5. And when I plugged it into the second term, I ended up with 768/8. So like I said, it's ugly, but it's not undoable, and I hope you're using a calculator to work all this out. Now, if we put all of this together, what we're actually going to end up with is 1/2 multiplied by, combine all these, and we'll get something like 4,569 over 40. And of course, that's not too difficult to work out. That's simply going to tell me 4,569 over 80. So that is the evaluation of this definite integral. Now, what does this look like? Well, if we look over here, yeah, there's a graph of it. There's the graph. It's almost triangular in nature. If we evaluate this from -8 up to -1, we're going to get this shape in here. And so, like I say, almost triangular in nature, although it certainly does have a curve to it. And so this thing has a pretty large area to it, and you can see that for yourself. We're going all the way back to -8, and this thing is flying all the way up to, I don't know what this is, maybe +16 or 17 or something along those lines. So if it were a rectangle, it would have a base of about 7, and a height of whatever this goes up to. But of course, we're only looking at a little less than half of that rectangle, 4,569/80ths. So there you go. Well, let's take a look at one more of these definite integral examples, one that involves trigonometry. So we know that that will be fun and exciting. Let's go ahead and take a look at that right now. All right, so for our last example dealing with evaluating definite integrals, we have this function here, 2t plus cosine t, that we're going to integrate from negative pi over 2 to positive pi over 2 and see what we get for that. Now, just because there's a trig function in here does not mean that this is going to be difficult. In fact, this is a pretty easy problem. If we integrate this, the antiderivative of 2t is simply t squared, and the antiderivative of cosine t is actually just going to be sine t. So that was not a difficult antiderivative to do, but if we evaluate this from negative pi halves to positive pi halves, let's see how this all works out. First off, what we'll have when we plug in our pi over 2 is we'll have pi squared over 4. That comes from the t squared. And then we have the sine of pi over 2, which, of course, the sine of pi over 2 is just 1. So there we go. There is substituting pi over 2. And now we need to subtract whatever happens when we plug in negative pi over 2. Of course, when we plug that into t squared, we're again going to get pi squared over 4. And when we substitute that into the sine of t, this time we'll get negative 1. So if we put all that together, of course, the pi squared over 4s are essentially going to cancel out, and we'll have 1 minus negative 1, which is just 2. Now, let's go ahead and take a look at what is going on here. There's the function, and I've already gone ahead and shaded in the area that we're looking at. Of course, this does involve having a negative area and a positive area, but when we put all those together, it does equal 2. Now, this is an interesting situation because we could build a rectangle that has exactly the same width as our interval and some height, and I'm not quite sure what that height is, but some height such that if we built this rectangle, that rectangle would have a height of 2. This isn't necessarily important for this problem, but where we're about to go, we're going to build these rectangles, and that's going to help us along. So, without further ado, let's take a look at the mean value theorem for integrals, and even more importantly, the average value of a function. Hopefully this makes sense when you think about what average means, but let's go ahead and formalize it now. The average value of a function is something that comes up quite often in calculus, especially when you'll be taking that AP test later on this year. So let's talk about the average value of a function, and once we discuss that, then we'll jump up and talk about what the mean value theorem for integrals actually is. Now, to begin this, let me go ahead and draw some random function here. And again, this will look similar to our last random function. I'm going to call it f of x. I just love the way this function looks. It covers everything. It's beautiful. So, the average value of a function. Let's say I want to know the average value of this function between this value a and this value b. What does average mean? Think about that. What does average mean? I add up everything and divide by however much there was. So basically, if I want to add up everything, what I'm talking about is adding up all the little rectangles that make up this area. And what would that be if I added it all up? Well, quite simply, it would be the definite integral from a to b of f of x dx. That would be the area of that red region. Now, if I want the average value of that, I just added them up. But what do I need to divide by? In other words, how much did I just add up? Well, that's actually pretty easy. If I just divide by b minus a, that's the width of the interval there. So I find the area and divide by however wide that interval is. That will tell me the average height of all these little rectangles all along this path. So there's actually a nicer way of saying the average value of a function. The way we usually write it is 1 over b minus a, that's the width of the interval, multiplied by the area within that interval. So average value of a function is usually written like this. And there you go. Notice, all we're doing is finding the area, adding up all the rectangles, that is, and then dividing by the width of the interval. No big deal. That will give us our average value of the function. Now, what is the mean value theorem for integrals? If we consider that this will give us a function f of c, that f of c is really going to help us with the mean value theorem, for integrals anyhow. Basically, all we need to do is find the area, which is quite simply done with the integral, and say that that equals f of c multiplied by the width of the interval. Now, can you see how we can go from the average value up to the mean value theorem? I essentially just multiplied b minus a on both sides. And what does this tell me? Well, right here, this is the width of our interval, or the width of all the rectangles added together. This is going to be the height of our average rectangle. And so what this is actually going to do is give us a rectangle that has the same area as what I was looking for earlier, but now it has the same width, but some height. And what that value of c is actually this value right here. It's where our function, our f, actually hits the top of that rectangle. That is going to tell us the mean value of this region. So f of c, if you want to look at this, f of c is the y value right there. Now this is a big mess, this picture I've drawn. It's confusing at best. But basically all I've done is I've taken the area that I'm looking for and turned it into a rectangle. The rectangle has the same width as our interval and some height that is attributable to the average value of that function. And so, while that might be a little bit confusing, I certainly encourage you to do some research. There's some great animations on the internet that will help to explain this. But this is the information we need in order to proceed to our next two examples. So let's go ahead and take a look at them now. And hopefully when we're done with examples D and E, you'll understand this mean value theorem and average value a little bit better. So let's go ahead and take a look at those. So examples D and E are actually two-part examples. We're going to begin on both of them by finding the average value of the function over the given interval. And then we're going to use the mean value theorem to try to find the value of c at which the rectangle with that average height is located. We'll use some graphics here, so hopefully this will all make sense in the end. But certainly we just need to find the average value of this problem to start. So, how are we going to do that? Well, let me go ahead and set this up. Average value is simply going to be 1 over b minus a, that's 1 over 3 minus 1, times the integral from 1 to 3 of our given function, 9 over x cubed dx. Now, you can see that I've shown you the graph of this function, and you see the shaded in area. That's what we're looking for the average value of. Now, of course, if I ignored this 1 over 3 minus 1 at the beginning, the integral itself will give us the shaded in area. This 1/2 will simply find the average value because our interval is, in fact, too wide. So let's see how this all works out. We'll end up with 1/2, and if I want to integrate this, what I can do, I don't want to integrate 9 over x cubed, but if I think of it as 9x to the negative third power, maybe that will be a little bit nicer to deal with. Let's see, if I do that, that would give me 9x to the negative second power divided by negative 2. And we're going to evaluate that from 1 to 3. Now, if I do that, I'm going to keep my 1/2 on the outside. But if I evaluate the inside of this, if I stick 3 in here, what I'll end up with is 9 over, let's see, this would be negative 18 on the bottom. And then I need to subtract whatever I get when I plug 1 into all this stuff. And that will simply be 9 over negative 2. Now, let me work this out here. 1/2 and negative 9/18 minus negative 9/2. Well, let's see. This is actually just negative 1/2 plus 9/2, and that's simply going to give us 4. 4, in fact, is the area of this shaded in region right there, and our average value is actually going to be just 2. Now, what does this average value mean? Well, if we look at all these little rectangles, there's one right here, and one right here, one right here, and even taller ones over here. But the average height of all of these rectangles is just 2. Now, I could use that interesting information to draw a rectangle here that's the same width as the interval, but has a height of 2. And in fact, what would be the area of this rectangle if it has a width of 2 and a height of 2? Well, of course, the area of that rectangle is just 4. And so the shaded in area and this rectangle have the same value. Now, you might be wondering to yourself, this rectangle doesn't look right. It should be a square, a width of 2 and height of 2. And in fact, it is a square. But if you notice, my axes are a little bit off, and I adjusted the axes so we could see this a little bit better. But rest assured, this shape here is a square. So there's our average value. Average value is 2. Now, the mean value theorem, what is that going to do for us? It's simply going to tell us what value of C our average rectangle is at. And how do I go about doing that? It really is not too difficult. What I'm going to do is I'm going to say somewhere, our actual function, which is 9 over x cubed, is going to equal that average value, which is 2. Now, I invite you to work this out yourself, but if you do it correctly, what you should get is that x is the cube root of 9 halves. And if we decimalize that, we'll see that this is equal to approximately 1.651. Does that look reasonable for our value of C, 1.651? To me, it certainly does. And it's at that value, x equals 1.651, that we're going to find our rectangle that has a height of 2. That's our average rectangle, and that is our mean value, the cube root of 9 halves. So hopefully through this example, you've seen how the area of this region can be reformed into a rectangle that has the same width as our interval, but some height that will allow the area of the rectangle to equal the area of our given region. Once we've done that, the mean value theorem says we can find our x value such that the height of our rectangle hits the function, and that right there is our mean value. Average value is just add up all the area, divide by the interval. The mean value is what place along the function we hit that average value. So there we go. It's a little bit confusing, but the more examples we do, the better it'll make sense. So let's take a look at one more example before we move on. So here's a fun and exciting little problem. We're given the function simply cosine of x over the interval from 0 to pi. And we need to find the average value of this. So let's just go ahead and get started. I'll skip the narrative. Our average value is simply going to be 1 over the width of the interval. Well, from 0 to pi, that is pi wide. So there we go. And we'll evaluate this interval, again, from 0 to pi of cosine x dx. Now, this is not a very difficult integral to do by any means. The integral of cosine is, in fact, just sine of x. And if we want to evaluate that from 0 to pi, what we'll end up with? Well, when we plug pi in there, of course, we'll get 0. And when we plug 0 in there, we'll also get 0. Looks like the average value of this function over this interval is simply pi. Now, we can, of course, as we did before, build a rectangle over this. It'll have a width of pi. It's going to go from 0 to pi. And it's going to have some height such that the area of this rectangle will equal 0. So how high is this rectangle going to need to be? Well, of course, this rectangle isn't going to have any height at all. So it has a width of pi and a height of, well, nothing. So if we now switch over to the mean value theorem, what I want to know is where along this equation's curve does it actually equal that average value? In other words, where does cosine x equal 0? And, of course, as you know, that's going to occur when x equals pi over 2. Again, does that make sense on this picture? I'll give you a hint. Pi over 2 is right here. And is that, in fact, where this curve hits 0? Of course it is. And so pi over 2 is our mean value based on the average value that we found to be 0. So there we go. That's how the average value theorem works. That's how the mean value theorem works. Both very useful, both pretty cool. And with that, we're going to now transition to talking about accumulating functions. I'll talk about it when we get there. Let's go ahead and begin with example F. So in our next two examples, we're going to take a look at what we call accumulating functions. These are functions that find the area from some given value up to x. And what we can do is fill in x if we want to know the value from wherever up to wherever. Now, why is this useful? Why can't we just evaluate the integral from wherever to whatever and be done? Well, if you take a look at example F, and G for that matter, they're wanting us to evaluate our integrals for x equals 2, for 5, and for 8. So do I want to do this integral 3 times for each of these different values? Quite honestly, I don't. And so what I'm going to do is I'm going to evaluate the integral once. It'll be in terms of x, and every time it'll evaluate the area starting at x equals 2 and going up to whatever value I'll put in. It'll give us an elementary algebraic function, which is easy enough, and I'll just stick in 2, 5, and 8 to find the respective areas. Now, this particular graph is going to look something like this. If these are my axes, it is negative, and what it will do is it'll go something like this. It is asymptotic to the x-axis, and actually it approaches the x-axis much quicker than I've drawn here. But for the sake of illustration, there we go. Now, if I call this x equals 2, then this question is asking me to evaluate the area from 2 up to 2, and then 5, and then 8. So, again, I could do this integral 3 times, but why bother? So watch how I'm going to do this. What I'm actually going to do is, if I evaluate this from 2 to x, I'm going to go ahead and pull out the negative 2, and what I'm left with inside is just t to the negative 3rd dt. Now, that's not a difficult integral to do. It'll simply be negative 2. This integral, t to the negative 3rd, is going to turn into t to the negative 2nd over negative 2, and I'll evaluate that from 2 to x. Now, as you can see, this negative 2 on the bottom is a constant and will cancel out with this negative 2 out here. And what I'm essentially going to end up with is x to the negative 2 minus 1/4. Where did 1/4 come in? Well, I just plugged 2 into t to the negative 2 and got this. In fact, if I wanted to, I could rewrite this as 1 over x squared minus 1/4. Now, what I can do is I can plug in 2, 5, and 8 into this elementary algebraic function, and that will tell me the area for each one of these. So let's go ahead and try that out. Let's see, capital F of 2 is simply going to be 1 over 2 squared minus 1/4. And let's see, that of course will give me 0. Now that only makes sense. If you remember our basic properties of integrals, when we integrate from a value to itself, we do get 0. So that makes perfect sense. Let's try this again, capital F of 5. Again, I could go up and reintegrate all this, going from 2 to 5, but why bother? I could just go from 1 over 5 squared minus 1/4, and if I work that out, it's simply going to tell me negative 21/100ths. And that is the area of this region here. Now, if I want to accumulate that further, let's say I want to go from 2 up to 8, that would simply be 1 over 8 squared minus 1/4. And again, that's not difficult to do. That's simply going to be negative 15/64ths. And that's going to be the area that's going to start at 2, go up to 5, and then continue on to 8. So I can evaluate any area. All I need to do is stick in the upper bound for x, because I already know my lower bound is going to be at 2. The 1/4 took care of that. So that's what an accumulating function is. It simply turns the integral into an algebraic function where I just need to put a value in for the upper bound, and it tells me the area. It's a beautiful thing, and it makes things a lot easier to deal with rather than having to do 3 separate integrals. So let's take a look at one more example, example G. Of course, I invite you to try this problem before we get to it, because we are going to get to it right now. So in example G, we're going to do the same thing we did back in example F. We have a different function this time, and I've drawn the graph for you. This is the graph of the square root of t. And as you can tell by this integral, for each area, we're going to start where x equals 4. So we'll start from that vertical line. Let's go ahead and begin by actually working this out. If we do, of course, I can rewrite this as the integral from 4 to x of t to the 1/2 dt. Maybe that'll make things easier, because the antiderivative of t to the 1/2 is simply going to be t to the 3/2 divided by 3/2. That's it. And I'm going to evaluate that from 4 to x. So what am I going to end up with here? My accumulating function, capital F of x, is actually just going to be 2/3 times x to the 3/2 minus whatever I get when I plug 4 in there. And when I plug 4 in there, hopefully I did this right, and I got 16/3. So here is our algebraic accumulating function. All I need to do is stick a value for x in there, and it will tell me the area of that region. So let's go ahead and begin. I'm going to do this first one in black. I'm going to color code this. This will be nice. If I start by evaluating capital F of 2, what I'm essentially doing is finding the area from 4 back to 2. So what should happen if I'm finding an area but going backwards? My first instinct is it's going to be a negative area since I am going backwards with it. But let's see. If I plug 2 in here, I'm going to have 2/3 times 2 to the 3/2, which is essentially just the square root of 8, minus 16/3. And if I decimalize that, that's actually going to come out to approximately negative 3.447. So it did come out to a negative area. Of course, there's no such thing as a negative area per se, but because I'm counting backwards, that's how that one works out. Well, let's try one more. This is going to be capital F of 5. This will give me the area from 4 up to 5. So it'll give me this blue area right here. Now, this time, I am counting forward, so I should have a positive area. But let's see what happens. This is going to be 2/3 times the square root of 125. That's 5 cubed, minus 16/3. And again, if I decimalize that, and if I did it correctly, I should have 2.120. And that makes sense. This blue area is less than this black area, the magnitude of it anyhow. But it is positive because I am going forward this time around. Well, let's do one more. This is going to be capital F of 8. This will find the area of the region starting at 4 and going all the way up here to 8. Of course, this will encompass the blue area, but it'll keep going up until I get to 8 right here. Now, I'm not very good at coloring things in on the computer, but hopefully you see the region that I'm talking about. It's a big region. I think it's going to have a big area, and it's definitely going to be positive. Let's see how this looks. We're going to have 2/3 times the square root of 512. That's 8 cubed, minus 16/3. And again, if I decimalize this, that's going to give me an area of 9.751. So significantly larger than either that black or that blue area, and certainly positive. So that's how accumulating functions work. I can just stick numbers in there. Those are my upper bounds. And the algebraic function will keep returning me the area of the region that I'm looking for. It's a beautiful thing, and it works quite well. But that begs the question. I wonder, what is the rate of change of this area? As in this example, if we start at 4 and continue up to 5 and then up to 8, and we could go even higher, what would be the rate of change of this area? Of course, you know that rate of change just means derivative. So really what we're doing is we're looking for the derivative of our accumulating function. Some of you might already have a thought in mind as to what this might be. But before we get to our last two examples, let's go ahead and formalize this. This is actually called the second fundamental theorem of calculus. Let's take a look. So once again, we're dealing with accumulating functions here. Now we're asking, what is the rate of change of this accumulating function? In other words, what is the derivative of the accumulating function? And it's actually very easy. If we're going to go ahead and integrate this and then differentiate our result, we're just going to come back right where we started. It's that easy. You can try it yourself. If you do, when we integrate this, we're going to get capital F of x subtracted by capital F of some lower bound that is a constant, that's a. And if we go ahead and differentiate this with respect to x, well, the derivative of capital F of x is just going to give us lowercase of x. And the derivative of this, which is a constant, remember, capital F of some constant is itself a constant. That's going to differentiate to 0. And so there's our general proof of why the derivative of an accumulating function is simply the integrand. Now, be very careful. The integrand is usually in terms of t, but once we differentiate it, we end up with that x inside. Now, that works great if we're if our accumulating function, rather, is going from some constant up to x. But what if we're going from some constant up to some function? Not necessarily x, but maybe it's x squared or x cubed or something like that. Well, things are going to work a little bit differently then. And so this is our generalized second fundamental theorem of calculus. It's very much the same, except this time we're going to have f of u, whatever u is, multiplied by the derivative of u. Why? Well, because that is the chain rule. So we'll have f of u times the derivative of u with respect to t. It's not too difficult, and if you actually work it out similar to our proof here, it does make sense. So try it yourself. Both of these are useful. The general version is more useful because it always applies, but in most cases, our accumulating function is just going from a constant up to x. And if that's the case, then our first version is much easier to use. So with that, let's take a look at our last two examples. We'll see the rate of change of an accumulating function. It will be fun. It will be exciting. Let's take a look. So let's do example H as if I had not yet shown you the second fundamental theorem of calculus. How would we evaluate this integral? Well, it wouldn't be too difficult. This is not a bad integral to do. I am going to rewrite it, however, as t to the 1/4 power dt. And now when we go ahead and handle this, what we're going to end up with is going to be t to the 5/4 divided by 5/4. And if we evaluate that from 1 to x, what we'll end up with is, of course, 4/5 x to the 5/4 minus, when I plug 1 in here, I just get 4/5. So that is capital F of x right there. Now, if I want to go ahead and differentiate capital F of x, what would that look like? Actually, it would not be very exciting. The derivative of this function right here, I'll keep my 4/5, but x to the 5/4, well, that'll become 5/4 x to the 1/4. And what's going to happen to the 4/5? It differentiates to 0. So if we go ahead and cancel out our 4/5 and 5/4, look what I end up with. X to the 1/4 power, aka the 4th root of x. Well, what does the second fundamental theorem of calculus tell us? It tells us that if we differentiate this accumulating function, we're going to come back right where we started, except we'll have an x as our variable instead of t. No big deal. There you go. So it's beautiful. You can do this by hand if you like, but hopefully the second fundamental calculus will save you a good deal of time. Let's take a look at one last example, example I, in which we're not integrating from a constant to x, but rather from a constant to x squared. What's going to happen when we differentiate that? Well, let's take a look. So here in our last example, we're going to try to find the rate of change of the accumulation function that's derived at by finding the integral of 1 over t cubed from 2 to x squared. Now, of course, just like in the last example, we can do this the long way or we can do this the short way. Why don't we start by doing it the long way just to see how all of this ends up? If we want to go ahead and integrate this, Of course, what we could do is refer to this as the integral from 2 to x squared of t to the negative third dt. That might make it easier to deal with, so that when we integrate this, what we'll actually get is t to the negative second over negative 2. And if we do our lower and upper bounds, plug both of those in, what we'll finally end up with is negative 1 over 2x to the fourth plus 1/8. Why plus 1/8? Well, it's actually minus negative 1/8, so I just took a shortcut there. Anyway, this is our accumulation function right there. If we want to go ahead and differentiate this accumulation function, well, maybe it would be a good idea to write this a little differently first. How about negative 1/2 x to the negative fourth plus 1/8? Now, this is going to be easy to differentiate. Shouldn't be too many problems here. If we use the general power rule and drop this negative 4 down, we'll get 2x to the negative fifth. And of course, the 1/8 is just going to differentiate away. So we could rewrite this and get our final answer as 2 over x to the fifth. That is the rate of change of our accumulation function. Now, interestingly, that doesn't look exactly like the function that we started with. In the last example, it did, but in this example, we're not just going from 2 to x, but rather from 2 to x squared. So we shouldn't expect it to look exactly the same as our integrand. Let's try this using the second fundamental theorem of calculus, just to see how this would work. I'm going to rewrite this as our accumulation function. Let's go from 2 to u of t to the negative third dt. And we'll do this with the understanding that u equals x cubed. Rather, u should equal x squared. That's our upper bound. Now, if we go ahead and use our second fundamental theorem of calculus, which I have written right here, and we are going to use the general form of this, what we're going to end up with is the derivative with respect to u of this function that we have right here. And this is going to be pretty cool, because what we're going to end up with is simply u to the negative third times du dx. So that's really going to be it. All I need to do at this point is just stick my u back in, and I'll have it. So what happens when I stick u back in? U is x squared. So what I'll have is x squared to the negative third times the derivative of x squared. That's 2x. And if we play around with that a little bit, this will give us 1 over x to the sixth multiplied by 2x, which simplifies to 2 over x to the fifth. So whichever way we do it, we're going to get the right answer. The trick of this is your AP exam writers know that you can do it the long way or the short way. So they will intentionally come up with problems that can only be evaluated using the second fundamental theorem of calculus. That being said, you better be careful. Know both ways of doing it, but understand that the second fundamental theorem of calculus makes things a lot easier, and in some cases, it's the only way of doing it at all. So here in lesson 4.4, we have covered a lot of things, a lot. We started by talking about the fundamental theorem of calculus, that is the first fundamental theorem of calculus. That was a way that we could evaluate definite integrals. Remember, definite integrals are integrals that have lower and upper bounds on them. So we're looking for the area from one value to another. That's opposed to indefinite integrals, where we just return a family of antiderivatives, always with a plus c. Definite integrals, on the other hand, never need a plus c, because we know their exact value by plugging in upper and lower bounds to the antiderivative. Pretty handy. Then, after we talked about definite integrals and did a few examples, we took a look at the average value of a function. And if you recall, average value meant we just add up all the area and divide by the width of the interval. No big deal. And based on our average value, we could take it one step further to the mean value theorem of integrals and find out at which x value the actual function hits the average value. There were all kinds of pictures we looked at and all kinds of stuff. Feel free to do your own research on that and try to make it make as much sense as possible, because it is a very common thing to see, and I guarantee you'll see it on the AP exam. Well, after talking about average and mean value theorems, we took a look at accumulating functions. These were functions that found the area of different regions, starting at a certain constant and coming up with an elementary algebraic function. Once we had that function, we could plug in any upper bound we wanted, and it was a quick, simple way to find the area of those regions. So accumulation functions are very useful, especially when you need to do the same integral multiple times. Just do that integral once with an upper bound of x, and then all you have to do is plug in values. Finally, we looked at the second fundamental theorem of calculus, in which we examined the rate of change of these accumulation functions. No surprise, we found that the derivative of an integral just returns us back to our original function. That is, so long as neither bound of the integral is a function itself. We took a look at a couple versions of the second fundamental theorem, and it does get a little hairy when our lower or upper bound is anything more than just an x. But if you remember our general version of the second fundamental theorem, it really isn't too bad. Of course, go back, take a look at your notes, and see that for yourself. So again, we have covered a lot of things. Keep your notes handy as you are working on the assignment for lesson 4.4. And as always, good luck.